right. Well, welcome back. This is part 2 of how to solve limits algebraically. We talked about the last time I gave this homework assignment, and hopefully you're going through and you know how to do everything up to about right here, and then all of a sudden you're like, what? What's going on here? How do I solve these types of limits? All right, how do I solve those limits? Because there are what we call transcendental functions. And, well, we're going to talk about that today. How to solve trig and exponential limits. So without further ado, let's get this party started. Whoop, whoop. A little review. We are going to be using this, so if you haven't written this down or don't know these, all right, they're kind of intuitive of how to use these properties of limits. Very, very similar as functions. So I'm not going to spend any more time on that one. But we will be using it when we solve some trig limits. Now, before we go and solve some trig limits, we're going to do a little review of trig by using direct substitution and applying the unit circle. So if you don't know the unit circle, okay, if you don't know the unit circle by heart, all right, that is what you need to study, my friends, because you need to be able to solve the limit of these functions lickety-split. So let's just do some quick review. And I'm going to show you also how to use the right triangles also to help you figure this out as well. So first off, we have the limit of tangent of x as x approaches pi. All right, as it approaches pi. Now, I'm just going to use this as a little review. So in our solve limit, we're going to see if its tangent is continuous at pi. Tangent is continuous at pi. Now, to figure out if tangent is continuous at pi, we're going to use direct substitution. All right, solve these limits. All right, so we're going to plug in tangent of pi into here. And if you don't know what tangent of pi is sine of pi, because that's what tangent is, sine over cosine of pi. Now, just help you out, all right, real quick, this is how I think about it. We have our unit circle, all right, we're talking about pi. Pi is located right here on the unit circle. What is that point? That point is going to be -1 and 0. If you recall, I always say sine of x equals y, sine y, cosine of x equals, or whatever this case, theta, all right, whatever the case may be, all right, equals x, all right, sine y, cosine x, all right, and that's the x and y value of the coordinate. So since we're plugging in pi, we're talking about right here, so we're talking about sine, which is y, the y value is 0, over -1, which is cosine x sine y, and so we have our answer is 0. Yeah, so it's continuous, and our answer is 0 for that one, just by plugging it in. Sine of pi over 2. So how do we figure this one out? Well, we got is we plug in 2 into there. So sine of pi, all right, times 2 over 2, which is just sine of pi. Well, what's sine of pi? Once again, all right, go over here, pi. I'm just going to keep on doing this because I think it's good just to repeat. All right, -1, 0, because that's what pi is. Pi is 180. Pi equals 180 degrees. All right, make sure we know that one as well. All right, sine y, what's the y value? That's going to equal 0. All right, that equals 0. Man, only 0? What? All right, try another one. Limit as cosine, or as x, cosine of x as x approaches 5 pi over 6. 5 pi over 6. All right, so we're going to use direct substitution. Direct substitution, plug it in there to figure out if it's continuous there. Cosine of 5, oops, forget the 5. 5 pi over 6. My 5s look like s's. I'm sorry. So what do we got here? Well, 5 pi over 6. 5 pi over 6. Pi over 6. All right. Make sure you know pi over 6, and that's all right. 180 degrees divided by 6, which actually equals then all right. 30 degrees, right? That's 30 degrees. So we're talking about 30-degree angle here, pi over 6, and we're talking about 5 of them. So 5 times 3 is 180 or 150. That's going to be over here. So this is a 30-degree angle for a reference. And that's going to give us, all right, which is the same thing as pi over 6, all right? I always convert my radians in degrees, all right, because it helps me. Maybe it'll help you as well. So this is actually going to be 5 pi over 6, which is equivalent to 150 degrees, which means this is a 30-degree angle. So I'm looking for this value right here, all right? I'm just going for cosine. Well, I just draw a little triangle. You can use the unit circle in the circle chart. It don't matter. All right, I know cosine is going to be the x value, all right, or you can just use SOHCAHTOA, all right, and I just go 1 radical 3 and 2 because that's a 30, 60, 90 triangle. All right, 1 is always up to the 30. Radical 3 is the adjacent, and 2 is the hypotenuse. This is negative because x is negative over here. All right, y is positive. All right, so we just worked it out. Cosine is going to be negative square root of 3 because that's a ka. Adjacent or hypotenuse is square root of 3 or 2. Okay. You could also get this. You want to do the unit circle, just divide everything by 2. All right, to make this radius 1, and so you have the y is 1/2, and this is going to be there. So if you want to do a unit circle, just divide everything by 2. All right, and we have a unit circle point. All right, of negative square root of 3 over 2 and 1/2. That would be the unit circle point, but we only care about cosine x, which is that one right there. Okay, so hopefully that makes a little sense. Hopefully it's good review. Know your circle chart. Know how to do it. You can use a triangle as well. It don't matter. All right. I use it to triangle. All right. Right here, we're going to plug this in here. So we have 7 pi over 6. 7 pi over 6 for secant. Secant is a reciprocal of cosine. This is actually 1 over cosine of 7 pi over 6. So 7 pi over 6, once again, pi over 6 is 30 degrees. 7 pi over 6 is going to be over here. It's a 30-degree angle. All right, this is going to be negative 1, negative square root of 3, and 2. It's negative because it goes down. Negative 1's over here because it's a 30-degree angle. This, just so you know, is 7 pi over 6. This whole angle right there is 7 pi over 6. Pi over 6, which is the same thing as 7 times 30 degrees, which is the same thing as 210 degrees if you want to follow along at home. Okay. And that's a degree right there. Okay, so when we have that, so what is the reciprocal of cosine? That's ka. So secant would be ha. All right, ha is a ratio, so hypotenuse, all right, over negative square root of 3, all right, which would be negative 2 square root of 3 over 3. How do we get that? Multiply top and bottom by negative square root of 3. All right, and we have those. Okay, so this is what you have to know how to do. All right, make sure you know your circle chart because you have to be able to find any of these different ones. It's going to save you a lot of time doing triangles or just memorizing it. That's what you need. Okay, so without further ado, let's apply this transcendental. Now, this is what we call transcendental functions. Transcendental functions are ones that are not algebraic. We did in our last video all the ones that were algebraic. Transcendental are ones that are not go beyond our understanding. Transcendental functions are like trig, exponential, and log functions. Not all the properties of algebra apply to trig functions. Okay, there is algebra that does apply, but trig is a ratio, and so you can't just distribute out the pi and so on and so forth. There are different rules that you need to apply to this. So, without further ado, the first thing is you want to make note, and you want to know these, and you want to write these down. Is we're going to look at these two different functions. All right, so we have the limit as x approaches 0 of sine of x over x. That's going to equal 1. Now, how do we know that? Well, if you take this right here, and I'm going to go over this. I'm going to pause this real quick and get back. And we're back. All right, as I said, I'm going to get Desmos ready. And I just put in sine of x over x. Now, like we do in all the other ones, you can look at this and figure out, okay, the limit as x approaches 0, because we're looking at when the limit approaches 0, okay, for this right here. All right, is that what is happening to our y values as we get closer and closer? Well, at 0, you notice it's undefined, okay, because sine of 0 is 0 over 0 is 0, okay? So it's an indeterminate form, okay, 0 over 0. Now, from here, as you can see, as we get closer and closer to 0, all right, these values appear to be approaching 1. So from the left, it goes to 1, and as right here, as you get closer and closer and closer to 0, it also appears, if you look at the y value, look at the y value, it's 0.998, it's getting closer and closer to 1 as well, all right? But yet, it's undefined at this value, but we know that doesn't really matter because limits are the intended height, whereas it's looking like it's getting close to, and not actually what it is. So in this case, we know that this limit is 1. We can do the same thing, all right, for cosine of x minus 1 over x. All right, and if I want to do that one, all right, create another expression. I'm going to go quantity cosine of x minus 1, all right, and we're going to divide that by x. Now, looking at this one, I'm going to get rid of this sign. You can look at this one as well, and you can see as we get closer and closer to 0, all right, you realize at 0, this value is undefined because cosine of 0 is 1. 1 minus 1 is 0. 0 over 0 is, all right, indeterminate form. It is undefined. So this value at 0 is undefined. But as you get closer and closer and closer to 0, it appears this is actually approaching 0. All right, you can see that graphically, and you can see that numerically. And go from the right side, goes to the same value, it's going to 0. It's going to 0. And therefore, we just verify this graphically and using a table, all right, that yes, these limits are what they say they are, 1 and 0. Now, those are important because we're going to use these limits to help us solve some more complex trigonometric limits, okay? Because we're going to use the property of limits to help us do this. So we're going to go through some problems to help us figure this out. All right, so first example, okay? First example, and I have several we're going to do. Sine of x over 2x squared minus x. Now, like you do with anything, you always want to do, no matter what type of function, try direct substitution, see if it's consistent. Probably no, it's not, but sine of 0, so we plug that in there. Sine of 0, all right, just so we know, the sine of 0, our point is right here. That's where 0 degrees is. Our point is 1, 0. Sine y is the y value, all right, and that's going to equal 0 right here. On the bottom, we plug in 0, and we can see that's going to be 0 minus 0, which is also over 0. Okay, so we have indeterminate form, just like the other ones. All right, so we have some removable discontinuity here. The question is, where is it going through? So we have to do some algebra. Well, can't use any conjugates, can't do any of this, but we are going to figure out, can we rearrange this and use what we see here? We have a sine of x. We know we have an x right here. Well, we're going to rearrange this and use property of limits. And I'm going to take out an x in the bottom. When we do that, we have 2x minus 1. Now, the property of limits, as I stated before, if you recall, we did this in the last tutorial, is that as you approach 0, to figure this out, we can separate this into two different limits. I can take the limit as x approaches 0, because I know the limit as sine of x over x, which is actually this portion right here, that actually equals 1. I can multiply that times the limit as x approaches 0 of 1, because sine times 1, all right, over the other limit, which is 2x minus 1. Well, doing so, I can find out both of these limits by going, all right, this limit right here, we know is 1. Times this limit, I can plug into here, I know is going to equal negative 1. So I plug in 0, 2 times 0 is 0, and we got that. And so 1 times negative 1 equals negative 1. Our limit for this particular function is negative 1. That's negative 1. And there we go. Pretty cool, huh? All right, let's try some more. All right, I'm going to move this one over here. I might need a little bit of extra room. It's a little bit harder one. All right, we'll go talk about later. All right, so let's focus on this one right here. All right, so if we have this right here, okay, all right, now let's try this one. If we have the limit, okay, of sine of 4x over x. Now, this is very, very similar to sine of x over x. Now, the problem is that we have 4x here. Now, this is what you need to know, okay? When we have this, whenever we have the limit as x approaches 0, and I have the sine of some sort of n, n is going to be any number times x. Now, if I had n, all right, x right there, and let's just say, okay, these two values inside and out, just like what we have right there, okay, were equal. Where does this limit go? Well, what we can do is I can find this limit by using what we call u substitution or a different value. So if I said limit, okay, and I said u, all right, equals nx, okay? Now, if I take this right here and say u equals nx, well, where would this go as x goes to 0? Well, as x goes to 0, all right, as x goes to 0, we know that this right here, all right, this would be 0 because as this is going to be 0, this is also approaching, u is going to be approaching 0 as well, okay? So these two values are going to be approaching 0. So u is going to be approaching 0, and this is going to be approaching 0. Now, next thing is, if I have the sine, and I'm going to replace nx, all right, with u, I have sine of u over u, okay? Well, as u goes to 0, well, now it's the same thing as we have up here. As u goes to 0, both of them are the same. So really, this limit's going to equal 1. So therefore, this also is going to equal 1. Now, you might be wondering yourself, hey, all right, why is that the way it is? Well, the reason why we want to know this is because if I can match the top and bottom here, I can then know that the limit's going to equal 1. So we're going to use a little algebra, a little math magic. All right, I'll just figure this out. Is that I want to have, if I had, all right, x approaching 0, if we had sine of 4x, and I had a 4x down here, I know that limit, according to this right here, this little proof, according to this right here, is going to equal 1. But we don't have a 4 down here. But can we make a 4 down there? Well, yes, we can. I can put a 4 down here as long as I multiply the numerator also by 4. Why is that? Because hopefully you're thinking to yourself, 4 over 4 equals 1, and I can multiply anything by 1. So as long as these two values, all right, I just put it in like that, all right, I can do this. I'm doing that because now I've created, all right, using the price of limits, what I can do, something I can solve. Because I know now the limit as x approaches 0 of sine of 4x over 4x, we know that's 1. And that's going to be multiplied by 4. Okay? Well, 4 times 1 is 4. And guess what? That's our limit. That's it. So whenever you have a value there, all right, we just multiply the other top right there. So for example, I'm just going to be a quick one. So if I hit a limit as x approaches 0 of sine of 5x over 2x, okay? Well, once again, I need sine of 5x. I have a 2. All right, can't solve that. All right, so I'm going to factor out the 2. I'm going to rewrite this as a limit as x approaches 0. I need a 5 in the bottom. So I'm going to have 5 sine of 5x. You cannot factor out the 5, just so you know. All right, I'm going to have 2 on the outside looking in. And I'm going to have 5x right here, because once again, I'm going to multiply by 1. Well, now by doing that, I know that these two are, what? That's equal 1. I have 5 halves times 1 now, which actually equals 5 halves. And that's my limit. All right. Well, let's try a little bit tougher one, okay? All right, this is very, very popular. You want to know this one, all right? All of these, all right? Using sine of x, all right? How to do that. Now, one more, okay? Let's get to a little tougher one. I'm going to try this on your lonesome, all right, first before we do this and see if you can get it. All right, you can pause it and go on. All right. Okay, so hopefully you tried it. So let's check this out. Well, once again, I have sine of 2 theta over sine of 3 theta. Now, this is a little complex. Now, this is what we're going to do. Well, if I had, I'm going to break this up into 2 different limits. All right. I have sine of theta, or say 2 theta right there. 2 theta right there. All right. Sine of 2 theta. All right. And I'm multiplying that by 1 over sine of 3 theta. Now, this is good because if I had 2 theta here, all right, and if I had 3 theta here, these two values would be equal, right? And we know, now even though this is reciprocal, all right, I can rewrite this right here and put it as x to the negative first power, so it's going to be the same thing. All right, that would equal 1. Okay, that would equal 1. These two values would equal 1. However, I just can't put a 2 theta there. I can't just put a 3 theta there, but I can multiply them by 1. If you notice right here, both this is a theta and a theta. Well, theta and theta, theta over theta is 1. Okay, so I actually can do that because theta over theta is 1. So I can actually add one of those there. Now the 2, I can't just put there, all right? So if I put a 2 there, I also have to put a 2 up here because that's not 2. If I put a 3 right there, I also have to put a 3 on the bottom, right? And I got that right there. Okay, so really, what's my answer going to be? Well, sine of 2 theta over theta is 1, so I have 2 times 1. This right here is the same thing, all right, as, well, that's going to be times 1 over 3 times, well, this is going to be the same thing as, if I put this to the negative first power, all right, let's see now right there, I can write this as sine of 3 theta over 3 theta to the negative first. What does negative first mean? That means reciprocal, because we have 1 over 3 to the negative first, just so everybody knows, that equals 3, right? So this is basically reciprocal. So essentially, these are the same thing. Well, we know the power property is I can find this limit, which is 1, and I'm just going to take that to the negative first power, which is, well, 1 to the reciprocal of 1 is 1. And so essentially, what is my limit going to equal? Well, looking at all this stuff, all right, I'm just going to erase this right now. I'm going to just go over here. All right, just use a different color. All right, so you can see that. So essentially then, what is my limit? Well, 2 times 1 times 1/3 times the reciprocal of 1 is going to equal 1/3. And that's our limit. Awesome, right? Yeah. Okay. In all these cases, what we did is we used this property, all right, or use this limit, this basic trig limit, sine of x over x, as x approaches 0, is equal to 1. And we use it for every single one of these cases. All right, let's try some other ones. This one, 1 minus cosine of x over x. Now, this is very, very similar to this one, okay? So can we, whenever you're given a problem like this, can we rearrange this into this property right here? Well, I need a -1, and this needs to be positive, so can I factor out a -1? Yes, we can. So if I factor out a -1, I'll have -3, and then I'll have cosine of x minus 1 all over x. And now if I take the limit as x approaches 0, once again, I'm using now this property. I know that the limit as x goes to 0, that's a constant, so it's going to be -3, times this one. Well, I know this limit is equal to 0. Well, 3 times 0 is 0. That's it. That's our limit. 0. Cool, huh? Let's try this one. Now this one's a little bit harder. I have cosine of x times tangent of x over x. Now, it might look like something like that cosine. Don't fret. Now, whenever you have this, usually students get really freaked out. But in trig, whenever you have tangent or anything else, all right, we first plug these values in here. All right, 0, cosine is 0. All right, and then tangent 0, direct substitution. Just make sure this actually works. All right, 0. It should be 0. Cosine of 0 is 1. Tangent of 0 is 0, because that's sine over cosine. And if you remember, 0 is over here. All right, that's 0 degrees. All right, 0 degrees, so it's 1, 0. Cosine of 0, cosine x sine y. That's our x value of our unit circle. So cosine is 1. Tangent is sine over cosine, so y over x. Remember, tangent of an angle is y over x, or sine cosine. Remember, sine y, cosine x. All right, so that's going to be 0 as well, because 0 over 1, and that's 0. All right, so we got that. Let's move all that stuff over here. All right. So what do we got here? So we have 0 over 0. Okay, 0 over 0. Okay, 0 over 0. 0. Now the question is, what do we do next? All right. Well, whenever you have 0, 0, and we're doing this, what I would do is get rid of tangent and make tangent into sine, cosine. Whenever you have sine, tangent, secant, cosecant, cotangent, write them in sine and cosine. Everything can be written as sine and cosine. So I'm going to write that as, well, that's tangent. Sine of x over cosine of x. That's the tangent, just so you know. All right, times cosine of x. That's going to be all over x. Now, hopefully you know something. Yeah, cosines cancel out. We then now have this. We can take the limit as x approaches 0. All right, and what do we have now? The limit as x approaches 0 of sine of x over x. Hey, we know that one. That one's 1. That's our answer. That's it. Using algebra. All right, simplify, cancel out. It's just that easy. All right. Turn something that's complex into something simple. That's what you want to do. All right. So those are a bunch of trig limits that should help you out. Always use your substitution. Use the unit circle. Know these basic ones. All right, and know how to apply them, and that can serve you well. Okay. All right. Let's try this one. Okay, one more. All right, last one. This will be fun. All right. So you have 1 minus tangent of theta. Okay. And pi over 4, pi over 4. So if you have pi over 4 is 45 degrees. All right, 45 degrees. 45 degrees is pi over 4, just so everybody knows. Pi over 4 degrees is pi over 4. And so we have a ratio of 1 to the 1 to the radical 2. Come on now. All right, and tangent is TOA. So it's going to be 1 minus 1. And that's going to be the square root of 2 over 2 minus the square root of 2 over 2. And then, 0 over 0. Okay, 0 over 0, not good. All right, we're going to pi over 4, so none of these will really apply, but let's see what we can do here. We have tangent. What did we say before? When we have tangent, we're going to simplify it. So we have 1 minus, let's make tangent sine cosine. So sine of theta over cosine theta. Right here, we have sine theta minus cosine of theta. Hey, we have a fraction over fraction. Recall in our last one, whenever we have a fraction over fraction, we want to make sure that we can eliminate the denominator. Okay, so I'm going to eliminate this denominator. I'm going to multiply top and bottom by the common denominator, which appears to be cosine. Cosine of theta. So I'm going to multiply top and bottom by cosine of theta. Now, when you do this, something really neat is going to happen. Okay? You distribute this right here. So what we have is cosine of theta minus, just read it here, where cosines cancel out, we're left with sine of theta. All over sine of theta, all right, minus cosine of theta, right? And that's times cosine. These are really close to each other. They're so close, I can smell it, all right? And I'm writing on an angle, I apologize. All right, so what we're gonna do is, this is really close. If they just change that, hey, I'm gonna factor out a negative. If I factor out a negative, I'll have cosine of theta minus sine of theta. And I factor out a negative, and I have negative. It's going to be, hey, it's going to be negative sine of theta, all right, plus cosine of theta. These two are equivalent now, times cosine of theta. Guess what? These are the same. I can cancel that and that. Those are the same. So now we have just eliminated our whole. We had indeterminate form before, right? We eliminated our whole. So what we have now is we're going to have negative, all right, I'm going to put the negative on top, negative 1 over cosine of theta. We can do that, all right, if you want to put 1 over negative cosine. All right, but I could, my right to put that on top, I could do that. All right, but you have that. Now, we're going to now take the limit as theta approaches pi over 4. Now, to make it a little bit nicer, this is the same thing as the limit as theta approaches pi over 4. What's 1 over cosine? 1 over cosine is cosecant, or sorry, it's secant, all right, of theta. So essentially, I'm finding secant of theta pi over 4. Once again, do pi over 4, all right, 1 to the 1 to the radical 2. Cosecant is ka, all right, our cosine is ka, so it'll be ha, adjacent over, or hypotenuse over adjacent, which gives us negative square root of 2. Negative square root of 2, all right, negative square root of 2. Just so you know, that's 45. Remember, 45-degree angle is the same thing as pi over 4. So I go back and forth multiply. All right. So there you go. Yeah. Awesome. All right. So that's our trig. Now, there's one other transcendental function we want to know. Make sure we know how to do. And in order to get these, we're going to talk about exponential logs. So it's really important that you review these exponential properties and log properties, because we're going to be using them to solve some of these problems in just a little bit. All right. Exponents and logs are inverse of each other. What does that mean? Inverse properties, essentially, we're going to talk about in just a little bit. All right, but they cancel each other out. Okay, but for exponents, all right, right here. Okay, and doing this. You know what I might do? I might actually do 2 different videos on this one. All right, so I'm going to stop here. I'm going to pick up, all right, on part 3 in just a little bit. All right, so hang tight, and I'm going to stop this, and I'm going to get started in just a little bit. All right, so.